normal damping force. Viscosity, normal velocity dependent viscosity is programmed in here. Okay, so it's now exponentially approaching the same velocity. We'll do this kind of problem later on, you know, with our calculus, things you can't do with simple ruler and compass. But you see, we've got most of the problem right now. It's just that we didn't realize that if there's a lot of give and a lot of friction, that this thing would actually go past that point and then return. That's kind of neat, right? I don't mention that in the text.
So what program is that you have? What language? What software?
It's called bouncing.
Oh, it's the second one on this list here, I think. Yeah, bounce it. We're going to use it a lot because, as you can see from the cover of this textbook, there's a bunch of balls making a tower there. We're going to have them bouncing all over the place. Many dimensions eventually, but just one dimension and lots of balls. This is a picture of the thing that we'll really be doing later on. Now that's an elastic collision there. So let's go ahead and do the elastic collision. It's the one that's actually simple.
Can we generalize this method to two-dimensional collisions?
Well, now we will do that. But it won't be this simple. Because you see, we're going to have only two conservation laws. Momentum and energy. Okay? And right now, momentum is a line and energy is an ellipse in this graph, which we have to prove shortly here. But later on, then, the conservation momentum, you see, that will be, well, actually be a plane, if we were to go to the next one, you see, and then the other thing would be an ellipsoid. So now there isn't just points where they intersect, there's a whole line that they can intersect on. It depends on what angle you were at, you see. Mm-hmm. So in that sense we can generalize it, but it won't be this simple. Now we have tricks for handling multi-piles. We'll do that later on. But so that's one way to increase the dimension and still use this geometry. Good question. Okay, anything else? I'll just go ahead and show the easy one by going back here to the controls and make this 0. I think I can type it in, can't I? Yes, that will work. And everything else the same. Let's see what happens. That should be enough, shouldn't it? Let's try. Bong! Okay, so that's pretty nice. That's you know, the ideal situation. Okay, I've turned the friction to 0. So to the aggregates computer, this is going to make it all the way to the circle on the other side, upper part of the circle.
Your velocities are displayed here too, if you want to look at it numerically.
Exactly, yes. Right,
C
right.
value we calculated.
That's what it's got right now. 90, that would be 90 in our units, right? And 40 for the V1. Yeah, let's see if that's right. V2, no, V2 is the VW, V1 is the SUV. Right, just exactly what you noted before. Okay, so we're at that point. All right. Now, I should say that if you're going to be talking about high speeds like this, crunch is pretty much going to be very close to the correct answer. But a kabong thing, if you just do a rescaling of this, I'm going to change geometry at all. I just change my units. 100 feet per minute. Okay, that's pretty slow. not walking speed, or strolling speed. 50 per minute is where they end up if the things were somehow to stick. If you had super glue or something on the two bumpers, you would bump and couldn't come apart, you'd end up at 50 feet per minute if you started at 10 feet for the Volkswagen, 10 feet per minute, and 60 feet per minute for the big heavy SUV. So that's where you would end up there if you had super glue. But if you had a good bumper that bounced perfectly, you'd end up very close to 40 feet per minute, 90 feet per minute. So the Volkswagen gets knocked out at enough speed in this parking lot collision. If it was going to keep going, in a minute it would go 90 feet. So just a couple miles an hour.
From this velocity plot, can we somehow calculate the coefficient of restitution?
We're going to try to do some of that. That's what the tensors are for. Tensor means tension, right? So we're going to, it helps you talk about the compression that's actually going on to make this happen. Yeah. It doesn't quite get what you want, but it comes close. Okay, now comments about ideal. Let's go through this really fast. Here's the actual road and the vehicles. Here's idealization 1, ignore the background, no rolling friction, air resistance, and most important of all, make H one-dimensional. Cars are constrained to ride on frictionless rail. There's an air track. This would be a good way to teach air track mechanics if you ever have to teach elementary physics. Everything's being done by geometry. I haven't brought out the quadratic equation. We haven't done anything that causes people to stop thinking about the physics and start thinking about, oh my gosh, what do I do with these formulas? It's two parts of the brain. You want to get one and then you want to get the other, and then you want to get them together. Okay? So that's what we claim is going on here. Now, later on in units 1 and 2, we're going to consider things that have 3 translational degrees of freedom. We're going to consider that before we get out of units 1, but unit 2 certainly is where we start looking at it. And you've seen the structure of your textbook. There's 12 chapters of the review section, and we're in chapter 1 of that, going on to chapter 2 now. And later on, if you read the preface, you find out how we connect stuff in units 1 to various places in the rest of the text. But there's also, in addition to 3 translational degrees, not just X, but Y and Z, these two say, we also have rotation. Okay? Now rotation to describe Euler angles, this is going to be our ruler and compass device when we get to talking about rotations. There are the 3 Euler angles displayed in a very physical way that makes a lot of sense and helps you do all sorts of things in quantum mechanics as well. And then finally, the SUV and VW will, have lots of other degrees of freedom, virtually an infinity of them. But if you're talking about, say, a molecule with 3 atoms or 2 atoms, okay, 2 particles, say this is an SUV, VW that have been attached to each other, how many degrees of vibrational freedom do you have? And it's it's the say n atoms have 3 times n. That's the degrees of freedom they have if they're just free, minus these 6. So these are called vibrational mode coordinates or something like that. And to handle those things, as we're going to see in units 2 and 3, generalized curvilinear coordinates of various kinds are the order of the day. And all the formulas you see on the wall there are mostly to do with GCC, generalized curvilinear coordinates. And we will talk about them in chapters 10 through 12, 10 and 12, a little bit in 11, which is the end of this review unit 1. So just giving you a heads up on how the plan is here to go through classical mechanics. Now, This 45-degree line that we're playing with here has a symmetry connotation, a very old one. The geometry of the Galilean translation is, I think, something you should pause and think about. Now, it's the law that gets finally broken at high speeds in relativity, but it's replaced by something that is very much like what we're thinking of as we do the old-fashioned physics of Galileo. As I say, we don't tackle this change of modern physics until Unit 8, and then we do it in a, as usual, extraordinary way. But I want you to think about what Galileo would have you believe, and that is that if you increase your velocity by 50 miles an hour, the rest of the world, I should say the rest of the universe, as he might say, appears to be 50 miles per hour slower in that direction. So if I'm looking at my class here of 2, 3, 4, whatever the number, and then maybe my colleagues outside there, and I'm frustrated that they're not going fast enough, I can change that easily. If I want them to be going 3 miles an hour that way, I start walking at 3 miles an hour. And there you go. You're all going 3 miles an hour now. Right? That's the Galilean idea. Right? Now, of course, it has a flaw. And that is the light which I'm using to look at you with is not obeying that. It totally ignores me at my 3 miles an hour. Doesn't subtract it, doesn't add it.
When you say that if you increase the velocity by 50 miles per hour, the rest of the world appears to be 50 miles per hour slower, that is from your frame, right?
That's from my frame, of course.
So you observe.
Who else would it be? Right? Like Ayn Rand, I'm a solipsist. The rest of the world doesn't exist. That's what Ayn Rand believed. And our economy is running on that principle. Unfortunately. Okay? So how on this chart do you account for a change in frame? If I want to use another frame, you see, what do I got to do? Well, I've got to subtract 50 from every point on there. I subtract 50 from that, and I subtract 50 from that, right? That makes me go down the 45-degree line. So this is a graph of a collision in this frame right here. If this is my origin, the collision is very symmetric, right? Here it's kind of weird, you know, from this point. Oh, this is the laboratory at the center of momentum. And it really is the center of a momentum. And that's what we need to talk about. So that's how you get to other frames. And I don't know whether this screen is in the view there, but I can go ahead on this computer here and bring that up. And there will be times when we really need two screens, so I might as well go ahead and get it out of the way now. I'll jump ahead here through our simple things and our idealization, which comes after this. And there's our 45-degree shift. And here's a few more. 5 or 6 other reference frames that are of interest. For example, the reference frame of the VW. Okay? Or this one I call SUV. In this one, the SUV has got some speed, but later on down here, let's see, this is the SUV axis. At this point, the VW is 50 miles an hour. The SUV is 0. You see the coordinate at that point right there. That's final, ending up with the SUV frame after the collision. This is before the collision using that particular frame that has the center momentum there. So these intercepts, the intercepts of these dashed lines that represent the final and initial values of a collision seen from one of these 6 frames are all on those in this region bracketed by the dashed lines of 45 degrees. Okay? So here's a point where SUV, I call it SUVI, that means initial SUV. He's sitting there with his, look at his his text on his cell phone, right? Everything is 0 miles per hour in that frame, so that's where he is. He's going to be here very shortly, right? In that frame, he's going to end up there, right? Then after he shakes his head and when he wakes up, he's now here. That's the new frame, right? For him, SUV, this is SUV final. Okay? So you see, this is a roadmap of all of the things that are going on from different viewpoints of this simple collision. Whether it's inelastic, crunch, or elastic, kabong, those are final points for that. It's all there, you see. That's the real, I think, advantage of the geometrical approach, is that you're getting a roadmap while you're solving it and showing you what to do next and suggesting what you do next more easily sometimes than algebra does. But we need to compare the algebraic stuff with that. So let me move ahead on this one to that point and talk about time reversal symmetry. Here's what we were just looking at, reduced in size. Here are all the time reversal pairs. I go from this one by flipping the velocity. The velocity is a derivative with respect to time. And time reversal means just change time to minus time. Don't touch any other dimension, including the x dimension that we have here. So I was simply taking minus of both components of this to get the time reversal thing. So the VW final down here situation is the time reverse of this. If I play the movie backwards for these collisions, this one right here starts here, you see, ends here. The time reversal of this is that one, and that's a final. You see, when you play time backwards, initial becomes final, right? And then this guy right here, the final, becomes the initial. But there's only one of them on there that's really got the symmetry, and that's the COM frame. This is unique. Now, initial is just opposite of final. There are not 2 points involved. So the picture in the COM frame is the VW coming in really fast and the SUV moving the other way, right? So I should turn this around because the SUV is on this side. So it's the VW, approaching the center very fast. The SUV approaches 4 times slower. Then they have a collision, and if it's elastic, they're not going to just sit here. They're going to spring back out again. This one out at 1/4 the speed of this one. So when you take a movie of that, time reversed, you can't tell which way time is. That's true of the other ones too. If you're really making it out to the circle, you've got time reversal symmetry to the accuracy of the collision.
This graph that you have drawn, the board, is we have solved this problem on lap frame, right? As an observer, stationary observer standing outside observing the collision.
This guy here, that would be home, right?
Yeah.
0 velocity.
Yeah.
The person that drew this graph,
Yeah.
us, the lab.
Like was sitting at the origin
Right.
and observing the process.
Yes, call that the lab.
But
And then this is the actual participants the scenario.
But if you want to solve the same problem in the center of mass frame,
Sure.
that we know how to do it algebraically by subtracting the center of mass velocity from the initial
Yes,
velocity.
subtract 50 in this case from both your velocities, and later on all 6 of them, right? If you're in 3 dimensions. Okay, so that's something that will carry forward to collisions in multi-dimensions. Yeah.
But if you want to draw the graph, solve the whole problem graphically in center of mass frame, how do you rescale the velocities? How do you go about doing that?
Well, let's answer that question algebraically, because that's the next thing we have to do here.
Okay.
Is look at the algebraic connections for this thing. Okay, let's go ahead here. So here's the vector algebra first of the situation, and all I'm doing here, if you want if you see, is I'm indicating the initial configuration of this collision scenario by a vector. And I put a little, head on the vector, right? Okay? So that would be a vector of V, how they either put an arrow over the top of it or draw it with a fat line, right? This would be the V N input, okay? Initial, all right? Same thing with this point up here. So that then puts us in the realm of vector analysis and finally tensor analysis for any operator that changes these things or represents a change, you see. So here would be a V fin, final. It's a vector. It has 2 components, an SUV component and a VW component, okay? V1 and V2, or Vx and Vy, is what we're looking at here. Now, it's of course a parallelogram, so if you're going to finish this diagram nicely for somebody that likes geometry, you see what you've got to do is you've got to take this vector right here, okay, whatever that is, you should make a little arc there, and then draw up here an arc, okay? And then I've got to take this vector right here, which is a little longer, and it's almost too long for this compass, but I can still do that. And then I put it on the other vector and strike an arc, and it should go right there, okay? It's a little off, okay? Looks like I'm here, I should be here, so I'll just make the point fat, okay? Cover up my, inaccuracies of this board and other things. Geometry is good to about 1 figure on this board. With the fine graph paper that we'll use, you can get 2 figures pretty easily. Getting 3 is really a challenge. So it gives you some appreciation, and I think if you're going to be teachers later on, everybody's imbued with these wonderful calculators. The default calculator is 13 figures. 13 figures! Oh my gosh, how precise, unimaginably precise that is. So, that's one of the things that geometry does. But in any case, you end up with a parallelogram going from here to here. It's just that vector moved up to the top there. So I'll just sketch that in just for the sake of symmetry. But later on, you'll be doing this and finding some other things out. Okay, so that's this graph right here that we're working with. Now, these are the velocity vectors that I want to define. We've done this one and this one. Don't forget that one. Okay?
So,
That one right here. And I'll go ahead and put an arrowhead on this thing right here. That one is VCOM. Center of momentum. Not center of mass, we're not talking about position here, we're talking about momentum and velocity. Okay, so these are the, now these components happen to be equal. These are. And that we have to make a point of. So, points of vectors, these three vectors, lie on the momentum conservation line. Okay? And this is the expression of the conservation equations. That is M SUV, V SUV, input, and then the input or initial of the VW product of mass and velocity. That sum is a constant. It's the same for the initial as it is for the final. Okay? But at any moment in between here, it's also true, including that moment right there, when it's at the VCOM. Because both the SUV and VW at that point have to have the same velocity. So there's the sum of the masses times the velocity there. Okay? So here's our momentum conservation, and this is expressing the number that you actually are conserving in terms of this thing here. That is the sort of the center of this geometry. Now, if this is a totally elastic collision, VCOM will be in the center of the parallelogram. This will equal that, this will equal that. It's dead center. And that's really why I want to get the parallelogram into the act here.
and so this holds good only it happens to be a parallelogram, right?
Say that again.
No, this one, the VCOM equals V initial plus V final by 2. That holds
This is
good
a very special condition.
only if you end up getting a parallelogram.
That's the Kabong situation. Otherwise, not so. Any loss to the insurance company or whatever, collision damage, gonna ruin that.
And geometrically, that's because the diagonals of a parallelogram bisect each other.
Yes, exactly. Good point. Okay. Now, we can massage these equations to do this. This is an interesting exercise. If I divide by the total mass, SUV plus VW, that momentum quantity that's conserved, what I'm saying is that the weighted average of any point on this line, but let's take the initial first and the final second. The weighted average of those coordinates, and weighted I mean weight of SUV and weight of the mass really of VW, but let's just call it weight because the mathematicians call it a weighted average and they don't really mean weight either. We mean mass, okay? And that average, in other words, I'm looking at what is the SUV and VW weighted average. Well, it's right there. Okay? And it's if I do the weighted average of these components up here, same thing. Okay, so all along here, the weighted mean is the same. This quantity. I just throw that out because, you know, if you want to think about weighted averages for other purposes, it means there's a geometry behind it. You can see it very clearly here. It'll be harder to see in 3 and even 4, but it's still there. Now we're going to take another tact. I used that tact before, and I actually have in the text written the old-fashioned way to prove energy. It has a terrible logical flaw, which it manages to have two wrongs that make a right. But if we go this tensor route with these vectors, we avoid that pitfall, that logical pitfall. It's also very useful for what we're going to do later. What we're really working with, what we're after here, is what a Lagrangian function is, and that's what we're getting at very quickly here. Now, here are the two vectors, 40, 90 that we ended up with in the final state, 60, 10, which is what we started with down there. And if we had a crunch, we would have wound up right here with VCOM equal to 50. Okay? Just to refresh your memory. Does that make sense? Okay? Now what I want to do is I want to sum the m times velocities for the VW and SUV initially, and I want to do the same for the final. To do that, also I can do it right here with a VCOM, I define a funny unit vector. Now this is not a unit vector. I have to divide by the square root of 2 in order to make that thing a unit norm. But I call it a unit vector because it's got 2 units in its components, and when we take the dot product with that thing, this is where we start doing our tensor algebra. So this funny unit vector, this thing right here, if you dot it with these combinations here, in other words, that's what I want to do. I want to do m dot v, just like that. That is going to be the sum of the momentum components. Momentum of SUV, momentum of the VW, final, or initial, whichever, okay? But I want to, at any moment, have a track. I want to track these two momentum. As the collision occurs, bang, or crunch, kabong, crunch, or kawum, whichever. I want to track those
Dr.
guys.
Harter, that funny unit vector is introduced just to construct the center of mass velocity matrix, right?
I just want to take a thing that I can dot this thing and get a sum. Let's go ahead and go on to the next step here. You see, the idea is to give a momentum vector whose sum of components is constant. That is, I do a u dot product here, I will get the sum of that. I'll get a sum of this. This is this times that, this times that, right? In other words, I'm going to do u dot m dot v, where v is any vector on that line there, okay, including vn, that's the initial one, and v fin, that's this one. And I'm going to use the u to sum them up, because this will be the constant that we're talking about, this sum right here. It'll be proportional